So this question is asking us to say where the function f of x is concave down. A function is concave down if the slopes are decreasing. Okay, we're not saying whether the slopes are positive or negative. Concavity is talking about how fast the slopes are changing. So for a function to be concave down, it means that the slopes have to be decreasing. So it's like the slopes of the slopes. If you were to graph the original function, you could look at some instantaneous slopes, figure whether they're positive or negative, but concavity is whether the positive slope is getting less steep. That would be concave down. Okay, so they actually didn't give us f of x, they gave us the derivative. So this represents a bunch of slopes. At x equals -5, the slope looks to be about 1.5 in the original function. At x equals -4, the slope of the original function is 2.5. So when are the slopes decreasing? Well, at x equals -4, we reach a turning point. We start going down, right? Before that, the slopes are going up. It's a pretty negative slope here, -7, -6, -5. The slopes are negative, but they're increasing because they're going up. Slopes are going up, slopes are going up. This is concave up until we hit x equals -4. And now, since this is the derivative, the slopes are going down. The slopes are decreasing, 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 decreasing. So it's concave down between x equals -4 and x equals 0. X equals 0 to x equals 4, though, it's concave up. The slopes are going up. And then x equals 4 to positive infinity, it looks like it's concave down because the slopes are decreasing. So -4 to 0. And then we need our union operator. And then we said -4 to 0. And then from 4 to infinity because the slopes are going down, starting at 4. And then we use a parentheses. Because at exactly 4, it's neither concave up nor concave down. Okay, this is not a graph of the first derivative. This is a graph of the second derivative. So what interval is it concave down? The second derivative means you're looking at acceleration. You're looking at the slope of the slopes. Here, and actually, let me write that out. You're concave down if the second derivative is negative, if it's less than 0. You're concave up if the second derivative is greater than 0. So this means concave down, and this means concave up. And that's what we were doing with that last graph, but we were looking at the first derivative, so we needed to look at the rate of change of those slopes. With this graph, we're given the second derivative. So where is it concave down? Between -3 and 1, we have negative slopes. The second derivative is less than 0. So it's concave down between -3 and 1. And where else is this graph negative? Between 5 and positive infinity. So we need a union. And then 5 to infinity is concave down because we are negative in the second derivative. So concavity is dealing with the second derivative.